Welcome back, folks. Second part of microfilaments, and I want to look a little bit at the mathematics of the dynamics of microfilament polymerization, just like we did with microtubules, so it shouldn't be too uncommon for you. It'll be pretty quick, it'll be a nice short one. So with microtubules, we talk about nucleation driven by gamma tubulin in the gamma-Turk complex. Now, that doesn't happen with actin filaments, although there is a nucleation phase. So in the initial nucleation phase, which is up here in the top left and is shown down here in the graph in the bottom left, ATP G-actin monomers slowly begin to form stable complexes of actin. So these nuclei of G-actin associated with ATP, and I have to say that slowly because there are multiple pieces or with a lot of A's in it, they begin to rapidly elongate as long as the free G-actin with ATP bound is above the critical concentration. So we still have this concept of critical concentration, which is the concentration which determines whether you get polymerization or depolymerization. So we get this elongation. Until then, in the third phase, the ends of the filament are in a kind of a steady, stable state with monomeric actin associating and dissociating. And then, just like we saw with microtubules, if the concentration of free actin drops below the critical concentration for the plus or the minus end, and those are different as well, just like we saw in microtubules, then we will get depolymerization, and if the concentration of G-actin with ATP goes above, then we will get polymerization. So we can see that the time course of the in vitro polymerization reaction reveals this initial lag, and then we have that's associated with nucleation. Then we have the rapid elongation, and then we see steady state levels. And so here we're seeing the mass of the filaments versus the mass of free actin, but you could probably plot what the mass of free actin would look like. It would look something like the inverse of what we have for the mass of the filaments. So if we add some short, stable actin filament fragments to the start of the reaction to act as nuclei, then we completely eliminate that elongation phase that we saw over here, and we go straight into elongation. So that's like adding gamma tubulin, because it promotes rapid elongation, and so those little short fragments would act like nuclei, much like the gamma-Turk did, and we've lost that lag period. Okay, so let's take a look at what's happening at each end here in respect to the association and dissociation constant. And is what this will reveal to us is that actin filaments can treadmill like microtubules do, and in their treadmilling they can actually do some work, because we're going to have some hydrolysis of ATP, and that's associated with a negative delta G. So actually treadmilling microfilaments can actually do some work in the cell, which is probably a little bit weird to think about. So generally speaking, we're going to find that actin subunits are going to add faster to the plus end than they will to the minus end, and that's going to end up giving us the phenomena of treadmilling. So let's look at what's going on with these numbers, because the numbers look a little bit kind of scary. Don't worry too much about the units here, except as what we will see is that the units will cancel out to give us a critical concentration in micromolar in a moment. So let's look at the association constants at the plus end and the minus end. So that's this figure at the top here, 12 micromolar minus 1, second minus 1. So that value there is nearly an order of magnitude greater than the association constant for ATP bound G-actin at the minus end. So there's a big difference. The association rate at the plus end is much higher than down here. And let's look at the dissociation rate. That's the rate that the actin comes off at the ends. So here it's 0.8 per second, and here it's 1.4 per second. So these are nearly the same, to be honest. Yeah, this is about 50% less than this, but given the magnitude difference between the on rates compared to the off rates, is what we see is that we will end up with faster addition of the plus end than the minus end. How do we get there? If we work out what the critical concentration for the plus end is, and you remember I keep saying that there's a different critical concentration for the plus end versus the minus end. Here's how we get there. If we calculate the critical concentration of the plus end, we do that by dividing the off rate by the on rate, and that gives us 0.12 micromolar. So that's the critical concentration for the plus end. Don't forget what that means. So what that means is if the concentration of free ATP-bound G-actin is above 0.12 micromolar, we are going to get polymerization of the plus end. And if it's below that, then we're going to get depolymerization. So there is our critical concentration at the plus end. And here is our critical concentration at the minus end. So we're going to do 0.8. Thanks, Eddie. We're going to do 0.8 over 1.3, and that's going to come out as a critical concentration of 0.6. So let's just think about a free actin concentration of 0.3 micromolar. So at that concentration, 0.3 micromolar is greater than 0.12, so we will get addition at this end. So we add in, imagine this actin subunit was blue, so follow these ones here. So imagine under those conditions of a critical concentration of 0.12 micromolar at the plus end and a free actin concentration of 0.3 micromolar, is what would happen is we would keep adding subunits to the plus end. Now bear in mind, as we do that, the free actin concentration is going to change, but as long as that 0.3 stays above 0.12, then we will keep adding. Now down here though, 0.3 is less than 0.6, so down here the free actin concentration is less than the critical concentration of 0.6, so at this end we're going to get loss. So even though we are depleting free actin from this end, when we add at this end, we're liberating free actin at this end due to depolymerization. So what will happen is these two blue, they're obviously not blue really, like I said, for tubulin, these two marked actin subunits will end up treadmilling through the microfilament until they eventually be lost at the other end. Now, what we end up with is at this plus end, we end up with a cap of ATP actin, but as the actin moves through the filament, it hydrolyzes its ATP to ADP, and it keeps the phosphate bound. So there's a region of ADP bound to phosphate associated with the actin. The phosphorus is lost, and we end up with a region of ADP actin. So as we move away from the plus end towards the minus end, we get more of these ADP actin form. So is what's happening here. The treadmilling really is a form of release of free energy. So delta G for this process is going to end up being negative, which means these microfilaments can do some work. They could move things. If we attach something down here and move it along, we can do some work, maybe some mechanical work of moving something. So that's how we can look quantitatively at what is happening at each end of these microfilaments. Okay, that's it for now. I'll be back soon.